Hi, today Andrew and I are going to talk about Commo, a cluster-optimized MMO game server. In traditional multiplayer game design, the server is the bottleneck and the single point of failure, because the server is a limiting factor in the number of clients that can connect and has to manage all the game state for all of the clients. Commo is a semi-decentralized game protocol, where clients also have to act as servers, but the master server is still used as a service discovery. One of the key properties that we want to exploit in Commo is proximity. Specifically, clients are probably more likely to care about messages from clients that are close by within the game space. This is to reduce the communication bottleneck, and this is a pretty realistic assumption because in most games you can only interact with players that are within some range or relatively close by to you. So in Commo, the clusters that we form are more like shards, where the game is also sharded based on location, and clients that are close by join each other in the same shard. Because this is still a decentralized protocol, there are still some concerns around reliability. So specifically, if one of the clients leaves, we don't want the whole game to grind to a halt. So our very simple game implementation involves a character that can move around in a 2D board and can also attack and heal those other clients that are within some proximity range, which is the green circle illustrated here. This is what it actually looks like in the demo that Andrew will show in a few minutes. So the key idea behind our decentralized design is at the game start, we divide up the board into shards, and each client is assigned to be initially in one of the shards. As they move around, they can dynamically switch which shard they belong to, but each client also holds a dual responsibility, as in it is potentially itself a shard server and it has to manage concurrency and consistency between all the actions that happen within that shard. However, because we use a Raft consensus protocol, we make sure that no one client is ever the single failure point for a shard. This is our diagram of roughly how Commo works. In this diagram, there are three different types of roles that a client can assume. They can either be a normal client with an additional responsibility of being a shard manager, so that means they're part of the Raft cluster responsible for some shard, not necessarily the same shard that they're currently in. The Raft cluster can also elect a shard leader. This leader is responsible for actually talking back to the master server from time to time to do some kind of health status. And you can also be a normal client with no sharding responsibilities. Usually if, for example, a client is too slow, we might not want to assign any additional networking responsibilities to that client. And the master server now acts simply as a service discovery for all the clients that want to join the game. So now we're going to walk through the Commo API protocol really briefly. So to begin with, all the clients first try to connect to the master server via the join game interface. This assigns them some kind of unique ID. Secondly, they get any kind of shard assignments. So the server might pick some of the shards to be, some of the clients to be responsible for certain shards, and some of the clients to not have to do any additional shard networking. Among the shard group, the Raft protocol then chooses one leader. The leader reports back to the master server that it has been chosen as the leader of a particular shard. Once the master server hears back from all the leaders, we can start the game. And keep in mind that as soon as every single client has called start game, they have a shard directory available to them, which they can then store locally. So that means if they ever switch shards or join a new shard, they know which hosts they can contact. So next, a client is assigned a shard based on its physical location in the game world. It asks to join that shard. It can talk to any of the clients that are acting as the shard servers. Once the game starts, each client can start taking actions within the game space. Again, this can be move, attack, heal. Via Raft, we replicate those actions and achieve consensus within the shard. If one of the nodes within the shard leaves, for example, some client just decides to quit the game, Raft can elect a new leader and notify the master server that it has now taken the leader responsibility. Finally, if the master server itself goes down, technically the game can continue. It won't be able to support any new clients joining. And if there are failures within the shards, it won't be able to update the global directory. But the game can continue in the current state. And within the normal course of the game, as the client moves around the game board, it can join different shards based on where its location is. And in that case, it would notify the current shard that it's leaving and ask to join one of the shard clients within the new shard that it wants to join. Cool. And with this, we're going to turn it over to Andrew, who will run through a quick demo of how this works.
So we start our demo off by showing the single server design of the game. This is really to get a sense of the game mechanics to see what the expectation should be. So we first start the server, and we have to allow it to accept incoming network connections. And now we start some random clients. So these random agents, they just move around the board randomly to populate the game space. Start some more of these random clients. Cool. Now let's start a player client. So a player client has a UI rendering to it, and the player client is a Pokeball. So the goal of the game is to catch Pikachus. And by what that means is that you want to get the Pikachu into the green proximity zone so that you can hit it and try to catch them. Unfortunately, these Pikachus are really fast. Alright, let's try to catch this one. So you can keep hitting it until it sort of dies, and for the sake of the game, let's just say that we caught it at that point. So you can see that when I try to click Pikachus outside my proximity zone, it doesn't work. So for fun, let's actually spin up just another player client so you can support multiple players. So sort of awkward windowing situation, but you can see that there's two clients now, and you can catch Pikachus together, have a competition, etc., etc. You can actually also try to kill the other Pokeball. And once you're dead, you cannot move anymore. Cool, so that's it for the single server design. Next we'll go to the decentralized version of this game. So here we show off our semi-decentralized design. To start off, what we need to do is spin up a server that's responsible for the initial shard assignment to the different clients, and also for service discovery during the game. So this is why the design is semi-decentralized, but the game mechanics themselves don't involve this server, as we will see later on. So right now, I will spin up some random agents to just really populate the game space, have something interesting to work with. And now I will spin up a player agent. So the game mechanics are exactly the same as a single server. The difference is that this game, as it's currently implemented, has 4 quadrants, basically 4 shards assigned to it. So this sharding can be flexible, but for the sake of this game, we have 4 shards. So the idea is that different clients are responsible for different shards of the game, and you can see that because this Pikachu can disappear between like boundaries. So you can see here I'm crossing different boundaries. The Pikachu is appearing, disappearing. In the final implementation, we hope to see all Pikachus within the proximity or near the proximity, but for now, this is a way to just visualize the different shards. So what we can see is that the game mechanics themselves still work as expected. I can show you as long as I catch up to that Pikachu. Oh, there's one here. Okay. So we can try to kill that Pikachu, and you can see that the game mechanics themselves still work. And on the left side here, you can see that the main server itself is not responsible for any of the game states. So let's spin up another player agent. So this other player agent acts as expected. Once it goes into the same quadrant as the other player, you can see that we're able to see it correctly. Another thing we want to do is let's try to kill the master server itself to really just prove the point that we don't need the master server to play the game. So you can see here, the master server has been killed, the game still works, and this just shows that the game itself is decentralized. Sure, no new players can join currently, but the current players, they will be able to enjoy this game even without this main server. And yeah, that's it for the decentralized server design demo.